Let me tell you about one of the simplest but most powerful ideas in problem solving. It's called the pigeonhole principle. So here's the story. Imagine you have 10 pigeons and only 9 pigeonholes. You try to place them neatly, but one pigeon in each hole. But then when you get to the last pigeon, it has no choice but to share a hole. So one hole at least ends up with 2 pigeons. That's the whole principle. So if you have more objects than boxes, at least one box has to hold more than one object. Now, this might sound almost too simple, but the magic is in how it shows up in puzzles and interview questions. So, whenever you see a problem that uses the words guarantee, must exist, at least one, or no matter what, that's your clue that it might be solved with the pigeonhole principle. So, we'll use the same 5 step playbook every time. First, count the objects. Second, prune the categories. So make sure you're counting the boxes correctly. Third, spread them as evenly as possible, like an adversary is trying to avoid a collision. Fourth, use the ceiling function to see the overflow. That is ceil bracket object divided by categories. And fifth is conclude what's guaranteed. So let's go through 6 classic problems together, which are also in the green book, which follow the same principle. Now imagine you have a drawer with socks, 2 red, 20 yellow, and 31 blue. You're drawing in the dark. So, what's the smallest number of socks you need to pull out to be absolutely sure you have at least one matching pair? So, let's solve this systematically with the same playbook. Step 1, count the objects. So, the objects are the socks you are drawing. Step 2, count the categories. The categories are the colors of the socks. So here there are 3 categories: red, yellow, and blue. Step 3 is spread. Now imagine an adversary who's trying to stop you from getting a pair. So what's the worst they can do? They can give you one red first, then one yellow, and then one blue. And after 3 draws, you have one of each color but still no pair. Step 4, sealing. So once you try to draw a fourth stock, there are no new categories left. You already have red, yellow, and blue. And the fourth stock must repeat one of those colors. So mathematically, it's like taking 4 socks into 3 boxes. So ceil 4 by 3 is 2, which means one color appears at least twice. And step 5 is conclusion. So the minimum number of draws to guarantee a pair is 4. So you see how guaranteed question follows the same playbook as the pigeonhole principle. Now here's a twist. What if the question asks how many draws to guarantee a yellow pair specifically? Now in that case, the adversary gives you all the non-yellow socks first. So 2 red plus 31 blue, that's 33 socks. Now at that point, you still don't have a single yellow. Then you would need to draw 2 more to force a yellow pair. So that makes 35 stocks total. So you see, it's the same playbook, but here the categories become yellow and non-yellow. Now the second problem, handshakes at a party. Let's switch to people. At a party with n people, prove at least 2 people shook the same number of hands. So step 1, count the objects, and here the objects are the people, so capital N equals small n. Step 2, count the categories. Now each person could have shaken between 0 and n minus 1 hands, excluding themselves. That looks like n possible categories. Step 3 is prune, but here's the catch. You cannot have both 0 and n minus 1 at the same time. So if someone shook hands with everybody, that is n minus 1, then there is nobody with 0 handshakes. If someone has 0, then nobody has n minus 1. So at most, n minus 1 categories are actually possible. Step 4, spread. Spread n people across at most n minus 1 categories. Step 5, sealing. Ceil n divided by n minus 1 equals 2, which means at least 2 people must fall into the same handshake count. And step 6, conclude. So in any party, no matter how many people shook hands, there will always be at least 2 people who shook hands with the same number of people. Now this one feels a little abstract, but it's the same idea. Too many objects, not enough boxes, and repeat is guaranteed. Now here's a famous problem. Among 6 people, show that there are always 3 who all know each other. or 3 who are all mutual strangers? Following the playbook, step 1, count the objects. So pick one person, let's call her Alice. She has 5 relationships to the others, and that's 5 objects. Step 2, count the categories. Each relationship is either knows or doesn't know. So there are 2 categories. Step 3, spread. Alice has 5 edges into 2 categories. So by the pigeonhole principle, at least 3 of those edges must be the same color, because seal 5 by 2 is 3. Step 4, sealing. So Alice either knows at least 3 people or she doesn't know at least 3 people. And step 5 is, if Alice knows 3 people, then among those 3, either some pair also know each other, which forms a triangle of acquaintances, or none of them know each other, which forms a triangle of strangers. And if Alice doesn't know 3 people, the exact same argument works with the colors flipped. So either way, we get a guaranteed triangle of 3. So that's why with 6 people, you cannot avoid creating either 3 mutual acquaintances or 3 mutual strangers. Now, let's go to geometry. Now, suppose you have 51 ants crawling on a unit square. You also have a circular glass with radius 1 by 7. Can you place the glass somewhere to guarantee that at least 3 ants are under it? Step 1 is count the objects. The objects are 51 ants. Step 2 is count the categories. We'll make categories by chopping the square into a grid now. If we use a 5 by 5 grid, that gives 25 little squares, each of side length 0.2, because it's a unit square, so 1 by 5. Prune. Now we have to check, can the glass cover one of these small squares? A circle of radius 1.7 has a diameter of about 0.28. The diagonal of 0.2 square is about 0.283. But the condition is that the side length must be less than or equal to r root 2. And r root 2 is about 0.202. And our square side is 0.2. So which just fits. So yes, each small square can be covered by the glass. Step 4, spread. Now spread 51 ants across 25 cells. In the worst case, the adversary places 2 ants in each cell. That makes 50 ants. And then the first ant forces one cell to hold three of the ants. Step 5, sealing. So seal 51 divided by 25 equals 3. So finally, there must be at least one cell with 3 ants. And since the glass can cover any one cell, you can always place it to cover those 3, guaranteed. Here's a clever one. You have 5 bags of coins. Each bag is either all 9 grams or all 10 grams or all 11 grams. You can take some coins from each bag once, weigh them all together once, and from that single number, figure out which bag is which. Step 1, count the objects. So each bag has 3 possibilities. With 5 bags, that's 3 raised to 5, 243 different scenarios. So we'll need 243 different scale readings to tell them apart. Step 2 in the playbook is count the categories. So the categories are the possible totals your weighing plan can produce. Step 3 is prune. If you design a weak plan, you won't have enough categories. So for example, you take 1 coin from bag 1, 2 from bag 2. Bag 1 could shift by -1, 0 or +1. Bag 2 could shift by -2, 0 or +2. So altogether, that gives only 7 distinct totals. But there are actually 9 possibilities across 2 bags. So the pigeonhole says that at least 2 scenarios collide. So you cannot tell them apart. Step 4, spread. So we need to create at least 243 categories. Now the trick is to take coins in powers of 3. So 1 from bag 1, 3 from bag 2, 9 from bag 3, 27 from bag 4, 81 from bag 5. Now step 5 is sealing. With this setup, each bag contributes negative, 0 or positive plus its weight. And together they form a 5-digit number in a system called balanced ternary. So that gives exactly 3 raised to 5, that's 243 distinct totals one for each scenario, and no collisions. Finally, one weighing is enough, but only if you choose your coin counts wisely. So, Pigeonhole told us why some strategies fail and why powers of three succeed. Now, here is a tricky one. Suppose you have 61 beetles on a board of size 2 by 1. You have a lid of radius 1 by 8. Can you guarantee covering 3 beetles with the lid? Now, following the same playbook, and we had asked this question in our Teaser Tuesdays on LinkedIn. So, following the same playbook, step 1 is counting the objects. As always, there are 61 beetles here. Step 2 is counting the categories. So, a category is a region small enough that one lid can cover it. The largest such region has a diameter of 0.25, which is the lid's diameter. And by geometry, the maximum area a lid-sized region can have is about 0.049. Then step 3 is pruning. So the board has an area of 2. So you need at least 2 by 0.049, which is about 41, such regions to cover it. The fourth step is spread. So the adversary could place 2 beetles in each of those 41 regions, which could cover up to 82 beetles without ever putting 3 in one region. And step 5 then is sealing. So seal 61 divided by 41, that's again 2. So now with 61 beetles, you can only guarantee 2 under the lid, not 3. So this is similar to the ants problem, of course, but unlike the ants problem, here the lid is actually too small relative to the board. So here, what's the big picture? Every problem we have solved, it used the same rhythm. We counted the objects, we counted or defined the categories, we pruned away impossible ones, we imagined an adversary spreading them evenly, we applied sealing to see where the overflow happens, and finally we translated that back into the problem's language. That is the pigeonhole principle. With socks, it gave us a guaranteed pair. With handshakes, it gave us equal counts. With 6 people, it gave us a guaranteed triangle. With ants, it gave us 3 in one cell. With coins, it showed us which plans fail and how powers of 3 work. And with beetles, it told us that there's no guarantee unless we have more beetles. One simple principle, but many disguises. And it shows up again and again in Quant Brain teasers. So I hope this identification of a pattern and a playbook style solution helped. Let me know if you have any questions. Until next time.